Hello everyone and welcome to Lesson 10, Images Formed by Lenses. Our goals for today will be to distinguish between converging and diverging lenses. We'll then draw three key refracted rays which will allow us to find the images in both types of lenses. And finally, we'll describe the characteristics of the image using the SALT acronym. Let's get started. In the picture below, we have a converging lens. The principal axis is the horizontal line that passes through the optical center. The optical center would be the center of the lens. We have to go through some terminology. Notice there's a point to the right of the lens labeled capital F. That's our focal point or principal focus. This is defined to be the point on the principal axis of the lens where parallel rays of light converge. And you can see this happening. To the left of the lens, we have incoming rays of parallel light. And as these rays of light hit the converging lens, the rays of light do as the name suggests and converge at the focal point. Next up, we have a point labeled F prime. It's F with an apostrophe. This is known as the secondary principal focus. It's a focus, but on the same side as the incident rays of light, as opposed to the other side of the lens. Let's actually label it in the picture. It should be at this location approximately right here. Okay, and like I said, it's the focus on the same side as the incident rays of light. Next up, we have the point labeled O. This is called the optical center. Okay, and it's defined to be the exact center of the lens. And lastly, PA, this is our principal axis. It's the straight line that passes through the center of the mirror or lens. Alright, and now with that terminology out of the way, we're going to learn how we find images in converging lenses. We're going to use three rays of light, and wherever those rays of light cross will be the location of the image. The first ray of light is one that passes parallel to the principal axis. We can see this in the picture below. When this ray of light hits the converging lens, it refracts and passes through the principal focus on the right side of the lens. So let's define it. And here's what it looks like. That incoming ray of light hits the lens, it refracts. Remember, that's the bending of light when it passes from one medium into another one. And in this case, it'll refract and pass through the focal point. Okay, and I'll keep the same color coding here to help us keep track of the different rays of light. The second one that we're going to look at is a ray of light that passes through F prime, our secondary principal focus. This one is refracted and comes out parallel to the principal axis. You can think of it like the opposite of ray number 1. We'll draw this in the picture below. So we have our incoming ray of light. This one passes through the secondary principal focus. It hits the lens, refracts, and comes out parallel to the principal axis. And the third ray of light that we're going to look at is a light ray that passes through the optical center of the lens. This one just continues traveling in a straight line without bending. So we'll show this in the picture to the right. This ray of light passes through O, the optical center of the lens, which I'll label as O, and it just continues traveling in a straight line without changing direction. So with your ruler, just extend the line, please, and we'll color code this one green. All right, and those are the 3 rays of light that we're going to use to locate images. Let's practice. So we have our object, which is a pencil. And to find the location of the image, let's draw those 3 rays of light. So the first one that I'll draw is a ray of light parallel to the principal axis. This one refracts and passes through the focal point. Okay, that's one. The second one that I'll draw passes through the optical center. And the third one that I'll draw passes through the secondary principal focus on the left side of the lens and comes out parallel. Okay, and this turned out quite well. The location where these 3 rays of light cross will be the location of our image. So it looks like it's approximately at this location here. We draw the inverted arrow to represent the image. Okay, everyone, so wherever the refracted rays of light converge is where we draw the image. All right, let's characterize the image now using the SALT acronym. First of all, the size is smaller. The attitude is inverted. As for the location, it's between F and 2F. By the way, F just represents the focal point, and 2F is twice the focal point. And as for the type of image, this one is real. So I just want to discuss this for a moment. Think about what lenses do. Lenses, for example, are found in glasses. The purpose of a lens is to allow light to pass through it. The lens bends the light, causing an image to form on the other side. If you think about glasses, this is exactly what you want the lens to do. You want it to take light coming from a source and bend it so the light forms somewhere on your eye. Whereas a mirror, rather than allowing light to pass through, the mirror will reflect light. So we would expect images to form on the other side of a lens, which is why this one is a real image. Okay, let's try another one. So now we have an object located at 2F. Let's go ahead and draw the 3 rays of light. So the first one that I'll draw is parallel to the principal axis. That one refracts and passes through the focal point. The second one that I'll draw passes through the optical center. And the third one that I'll draw passes through the secondary focal point and comes out parallel. And if you've done this properly and used a ruler, all of the light rays should converge at one point at approximately this location. Alright, now we characterize the image using the SALT acronym. It may not be clear from the picture, but you can verify this with a ruler. The size of the image is actually the same. The attitude, as we see, is inverted. The location is at 2F. It may not look that way from my picture, but it should be. And finally, the type of image, it's also real. Okay, let's continue practicing. Here we have an object between F and 2F. This would actually be a great time for you to pause the video, try it on your own, and when you're ready, click play to resume. Okay, let's draw our rays of light. So the first one that I'll sketch is parallel to the principal axis. And when it hits the lens, it converges, passing through F. Okay, and the second one that I'll draw passes through the optical center. Alright everyone, it's perfectly fine just to sketch 2. I mean, that's more than enough. We see where they cross. It appears to be at approximately this location, which is where our image will be. Okay, so in this case, the size of the image is larger. As for the attitude, it's inverted. The location is past or to the right of 2F. And this is a real image as well. All right, let's try this one. So now our object is inside of F. Okay, so I drew 2 rays of light, and you're going to notice something funny happens. They appear on the right side to be getting further apart. There's no way that these rays of light can converge if they're moving further and further away. So this is actually going to be the only time you produce a virtual image with a converging lens. You have to do that trick like we did with mirrors where you back trace the rays of light. Let me show you what I mean. For the red ray of light, just continue drawing a line backwards. Use the dotted line to differentiate it. And do the same thing with the blue ray of light. Okay, and you'll see that those dotted lines appear to cross at approximately this location. And that is where our image will appear to be. But by the way, whenever the object is to the right of F, that'll be the only scenario where you form a virtual image. In this case, the size is larger. Notice that it's upright. So virtual images will be upright, real images will be inverted. The location, you can say behind the lens, or to the left of the lens, as you prefer. And as I said, this would be a virtual image. Okay, one more to go. What happens when you place an object on the focal point? Let's find out. Okay, something funny starts to happen as well. Notice on the right side of the lens, the light rays are not getting closer together. And if you try to use your ruler to extend them, you're going to notice that they don't cross anywhere. These two rays of light are parallel. So they never meet, meaning we don't form an image at all. So the SALT acronym is irrelevant here, and we'll just make a note. No image is formed because the rays of light are parallel. All right, so now we're going to summarize. And we saw all of these cases when we were doing the examples. So let's get started with the object location. Anytime the object location is beyond 2f, the image will always be smaller, inverted, between f and 2f, and finally real. When we place the object at 2f, the size is the same. It's still inverted. The location is at 2f, on the other side of the lens, of course, and it's also a real image. When we place the object between 2f and f, the image was larger, inverted, it formed past 2f, and finally it was real as well. When we placed the object right at f, no image was formed. That was the last case that we did, so the SALT acronym is not applicable for this one. And lastly, when we placed the object inside of f, the image was larger, upright, it formed behind the lens, in other words, on the same side of the lens that the light was coming in from, and this was the only time that we formed a virtual image. Okay, everyone, that's about half the lesson. That's converging lenses. Now we're going to go on to diverging lenses. This is what a diverging lens looks like. I'll just kind of draw over it here to make the shape clear. Okay, so let's define all of the points now. It's pretty much exactly the same as before. F is still our principal focus. F prime is the secondary principal focus. O is our optical center. And PA, once again, is the principal axis. Okay, now it's time to find images in diverging lenses. Sorry, small typo here. Please change that from converging to diverging. Okay, so in a similar way, we're going to use three key rays of light, and the rules are very similar. The first ray of light is one that travels parallel to the principal axis. This one refracts, but rather than converging, the ray of light diverges. It's going to appear that it came from F. Let me show you what I mean. Here's our incoming ray of light parallel to the principal axis. It hits the diverging lens, and as the name suggests, it diverges, like this. Diverges means to move away or spread out. That ray of light is going to appear like it came from F. So just extend it using the dotted line. We've done this a few times now. Okay, and that's what we mean. It appears like it came from F. The second ray of light that we're going to draw is a ray of light that is heading towards F prime. It's refracted and comes out parallel. Okay, I'll show you what I mean. This one looks like it's heading towards F prime, so if you extend it, it's going to head towards F prime. But what the diverging lens does is refracts it, basically bends it away from the direction it was coming in so that it comes out parallel, like so. All right, and the third ray of light passes straight through the optical center. This one just continues in a straight line without bending. All right, and like before, wherever those three rays of light cross will be the location of our image. Let's do some practice. So we have our object to the left of 2F. Let's draw one ray of light parallel to the principal axis like so. This one refracts and it appears like it came from F, like this. Okay, that's number one. The second ray of light that I'll draw passes through the optical center like so. And the third one that I'll draw heads towards F prime. But it gets refracted and comes out parallel. All right, so look at your three rays of light on the right side and notice that they're all moving away from each other. So they're never going to cross. What we have to do is back trace the rays using the dotted line. And wherever the back traced rays cross is the location of the image. So Please don't mistake the location of the image to be here. That's where the dotted blue line crossed the solid green line. We want to look where the dotted lines cross. Because the red one that I drew just travels in a straight line, we want to look at where the red line crosses the two dotted lines. In my picture, it appears to be at approximately this location. So please draw an arrow where those three rays of light cross, and that'll be the location of our image, which we'll now characterize using salt. So you can see that it's smaller, upright. As for the location, it's behind the lens. And this would be a virtual image. Okay, so just a little rule over here. Whenever we're finding images, the refracted rays diverge, so we have to trace back the virtual rays. All right, let's try another one. So here we go. Let's draw a ray of light that heads towards F prime. This one gets refracted and comes out parallel to the principal axis. While we're at it, you can go ahead and backtrace the virtual ray. And the second one that I'll draw passes through the optical center. And honestly, everybody, that's enough. Look at where the red light crosses the dotted blue line. That'll be the location of your image. Right here. You really only need two to find the location of an image. Okay, the size is certainly smaller. The location again is behind or to the left of the lens. As for the attitude, it's upright. And this would be a virtual image. Let's continue practicing. Here we have an object to the left of 2F. So the first ray of light that I'll draw is one that comes in parallel to the principal axis. This one gets refracted and appears like it came from F. And the second one that I'll draw is my favorite. This one just passes through the optical center. And guess what? 2 is more than enough. Look at where the red line crosses the dotted blue line right here. All right, our image is smaller. Once again, it appears to be behind the lens or to the left of the lens. It's upright as well. And virtual. All right, just a few more to go. This would be a good time to pause the video, try it on your own, and when you're ready, click play to resume. You can pick any two of the three rays of light that we talked about earlier. This will be the first one that I draw. Okay, so this one comes in parallel to the principal axis, refracts, and appears like it came from F. And I'll draw my favorite one, which passes through O. And there you go, 2 is enough. Right, as for the image, it appears to be smaller, upright, behind the lens, and virtual. What happens when we place the object on F? Let's find out. Here's our first ray of light, parallel to the optical axis, parallel to the principal axis. It refracts and appears like it came from F. Okay, and here's the second one. All right, and the image forms right about here. Notice that the image is smaller, upright, behind the lens, and virtual. Do you remember what happened in a converging lens when we placed the object at the focal point? In that case, the rays of light never crossed, they all came out parallel, but this isn't so with the diverging lens. And I believe this is our last one. Here the object is located at 2F. So pick any 2 of the 3 rays of light and let's see where they cross. And look at that. Once again, the image is smaller, upright, behind the lens, and virtual. So everyone, images formed by diverging lenses are always going to share these 4 characteristics. That's true for all images formed by diverging lenses, but not so with images formed by converging lenses. Well, thank you very much everyone. I hope you enjoyed the video. If you have any questions, don't hesitate to reach out. Thanks, and we'll see you in the next one.